All right, remember when we started this lesson, we had this thing that I called an alternator. It was -1 raised to the nth power, or maybe the n plus 1th power, which essentially just alternated the signs of the terms of our sequence, positive, the negative, positive, and negative. Those are called alternating sequences. And specifically, it has to be one and then the other. It has to be like an on and then an off, an on and then an off. You can't have plus, plus, minus, minus, plus, plus, minus, minus. No, it has to be plus, minus, plus, minus, plus, minus, or minus plus minus plus minus plus. Okay, if that's the if that's the case, and we're trying to find whether or not our sequence converges, well, it's much easier to do if the terms of our sequence were not alternating. Okay, so we have a way around it, and it is this thing that is called the absolute value theorem. It's super important, and it's basically proven with the squeeze theorem, and we'll see that on our example that we illustrated with. So it can be shown that if the absolute value of the terms of our sequence converge to 0, then the original sequence, which alternates, also converges to 0. It's just that this one here is going to oscillate back and forth, but it's getting closer and closer to 0. Here, these are just going to decrease to 0, let's say. So here is the absolute value theorem, which goes for the sequence of a sub n if the limit as n approaches infinity of the absolute value of the terms of your sequence, the nth term of your sequence, is equal to 0, then the limit as n approaches infinity of the original sequence, which alternates, it has positive and negative terms in it, it's also equal to 0. So let's see that play out here in this next example. Show that c sub n, which is equal to -1 to the nth power, times 1 over n factorial, converges. So here we have our little alternator, which is going to take the terms of the sequence starting with n equals 1, and we have a negative term, then you have a positive one, a negative one, and a positive one. But we want to show that what is going to happen is that even though they're oscillating closer and closer to something. Okay, so this is the way that I tackle that. I am going to take the limit as n approaches infinity of the absolute value of -1 to the nth power times 1 over n factorial. Okay, so this n right here is a positive number. So this term right here is already positive. The only thing that is potentially negative is the alternator right here. And when I take the absolute value, it negates this whole thing. It like gets rid of it all completely. So this becomes the limit as n approaches infinity of just 1 over n factorial. We have 1, which is constant, over something that is getting increasingly larger. This is going to converge to 0, which means that the limit as n approaches infinity of the original one, which is -1 to the nth power, times 1 over n factorial, is also 0. So essentially, when we look at the graph here, these terms of the sequence are just going to decrease towards 0. These are going to oscillate, but they're going to oscillate closer to 0. All right, so let's take a look at a picture of the graph and see how the graph uses the squeeze theorem to demonstrate it. Okay, so our sequence is the one that is oscillating here, right? And then the squeeze theorem just says that you have to find a function that is down below, you have to find a sequence that's up above. And notice that this one, the one that they've chosen here, 1 over 2 to the nth power, is not always up above it here. It's not always down below it, but it does eventually get there, right? So after about this term here, then ours is completely sandwiched or squeezed in between those two values. If the top one approaches 0 and the bottom one approaches 0, then ours also approaches 0. We're not going to have to apply the squeeze theorem to it. The squeeze theorem is just what justifies the absolute value theorem. Instead, we just apply the absolute value theorem. Do we have negative terms in our sequence or alternating ones? We'll take the absolute value of the terms of the sequence, then take the limit and see if it approaches 0. Notice that this is just 0 right here. That's what the theorem says. That if the absolute value of those terms approach 0, then the original one also approaches 0.